All right, let's get started. Oh. Just so everybody's aware, I don't really have anything, like major in the way of announcements. Other than today, we are going to finish T-beams because we have one final example to do with T-beams, and that's we did a T-beam design example last time, and that was a rectangular T-beam. And so today we're going to do an example that ends up being a true T-beam. Spoiler alert. Then what we're going to do is we're going to get into doubly reinforced beams. And so if you recall, doubly reinforced beams is when not only do you have steel in tension, but you have steel in compression. And we'll talk about what that can do for you in terms of capacity and so on and so forth. Let me turn that. Next thing you know, it's going to say, you big noise popping up. So there's that. I did want to go ahead and pull this up. It's been a while since we've looked at this, and I sort of like to just make sure that everybody's got the whole picture sort of figured out. So first off, let me collapse these tools, and let me see if I can zoom in a little bit. I think that's a little better. So we are right here. We are sort of right there. Okay, well, that's about the best you're going to get out of me. By the way, I have not yet graded the exam. I've got a couple more that I need to grade, but I'm hoping to get you those exam grades by Wednesday. So apologies for that, but I should have the exams graded by Wednesday. So just so everybody is aware as to what's going on in terms of the schedule moving forward. So you all have homework 5 assigned now. That's the T-beam and doubly reinforced beam assignment. That's on Blackboard. It's not due until the 13th, okay? So today what we're going to do is we're going to finish T-beams, okay? We're going to finish T-beams. We're going to finish doubly reinforced beams. It's a pretty quick topic. I mean, actually the math can get a little intense because there's a lot that you've got to handle, but it's actually, in terms of the topic or the time in class, it's actually kind of quick because we don't have to design doubly reinforced beams, at least for this course. We just analyze them. But after that, we spend the remainder of our time between now and when spring break hits on shear, okay? Now, I did you all a little bit of a favor with this course. So homework 5 is due on the 13th, and then you get homework number 6. Homework number 6 is on shear, okay? So that homework is due the Friday before spring break. However, we're actually like very, very slightly ahead in terms of where we're at in class. So we can probably get to a point where we get shear design done a little early, okay? Then what we're going to do is this. So once shear design is done, you're done until we get back, okay? So I might, depending upon where we are at, if we finish shear design on Monday, maybe I'm nice and give you Wednesday off too. Maybe. Let me say this. I don't want to get like super lofty in my goals. I'd rather not promise you something I can't deliver. But I will say this. I will not start serviceability until we get back. I'm not going to do that. That's a whole new topic, and I don't see any value in starting it here. Say, okay, we'll talk about serviceability. Then you're going to forget it while you're out partying for the next 10 days. Then we'll come back and have to discuss it again. That doesn't make any sense. So, but we'll have to sort of move for that to happen. So I don't want to promise something that I can't deliver. But I can tell you when we're done with shear, we're done until we get back from spring break. Sound good? Okay, so with that, let me just sort of jump right into it so we can get a rockin' and a rolling. So let me jump back a few slides. So let's go here. Okay, so we're on T-beam design mode. So we've already been through one example. So hopefully what you're finding with this process is that it's pretty straightforward. It can be a little bit more intense, because the problem's a little bit bigger, and you have to determine whether or not it's a rectangular T-beam or a true T-beam. But it's a pretty straightforward process nonetheless. We start off, if we're in design mode, remember with T-beams, we're always dealing with a known cross-section. So all we have to do is determine the factored moments on the beam. We don't have to assume a beam self-weight for step 1. We assume a phi value of 0.9, and so at the very, 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 very end of the problem, theoretically, this is what you'd have to do, is verify this assumption. So assume a phi value is 0.9, bless you, and compute Mn required. Next, what we do is we have to figure out what type of beam that we're dealing with. So we start off assuming that the neutral axis is in the flange. We compute rho. Remember, rho is our reinforcement ratio. That's how much steel we're putting in the beam on a percentage basis. So we determine rho if it was a rectangular beam, and then we plug that rho value back in. And basically what we're saying is, if we used that much reinforcement, what would the depth of our stress block be? And so that tells us whether or not the assumption of whether or not we were dealing with a rectangular T-beam or a true T-beam is true. If we are dealing with a rectangular T-beam, then we just do rho BD, pick a steel pattern, move on. If not, if we're dealing with a true T-beam, then it doesn't get harder, it just gets a little longer. Remember, when we're computing a true T-beam's capacity, we split it up into a flange couple and a web couple. So the first thing that we do is we figure out everything associated with the flange couple. If you recall, here's the flange couple and the web couple, and the flange couple over here, this one over here on the left, is completely independent of A. And so not only does that, because it's independent of A, that's actually kind of important because it's actually completely independent of how much steel we put in the beam. So what we can do is we can say, all right, if it's a true T-beam, we compute the capacity of the flange couple, and then we determine how much steel we would need to put into that couple to make that happen. And then once we have the capacity of the flange couple, we then back calculate, well, how much capacity would we need out of the web couple? And once we get that, compute how much steel we need there, add the two steels up, and then pick a pattern accordingly. So there's a little bit more going on, but it's not harder, it's just a little bit longer. The only other thing I would like to mention with T-beams, and we haven't really broached this topic before, but it can kind of be a necessity with T-beams. T-beams, by their nature, are bigger. Okay? So because they're bigger, their nominal moment capacity is bigger. So because of that, typically to generate the required nominal capacity, we tend to have to put more steel in the beam than we would if it was rectangular. So I would argue that if there's ever a time where you probably need to start considering putting your steel in multiple layers, this is the time, okay? Because you got this really big beam, and then you have a web that's only this thin, and you got to fit all that steel in the bottom. So when we get into our example today, I'll show you how this is probably going to be the situation with this beam. So we did this example, and we found a steel area. It was something like 3.34 or something like that. And we picked a pattern that made sense, and there you go. Did anybody have any questions on that? Okay, so here's this problem. Again, one of the things I'm trying to do is I'm really trying to reduce this doing the same problem over and over and over again. So if you notice in 10A, one of the things I didn't give you in 10A is I didn't give you the effective flange width, and I didn't give you the moments on the beam. Well, I'm doing that on 10B. It is not in any way, shape, or form different than, or the process for determining the effective flange width of the moments. It's not in any way, shape, or form different than the last example, which is why I'm not making you do it again. We've done it once. We don't need to do it twice. So we have the effective flange width being 54 inches. The flange height's 3 inches. We know the effective depth's 24. And we just need to determine the steel. So, and we know the web width is 15 inches. So let me go here. Copy that in. Let me make that smaller because that is big. There we go. Okay, so here's example 10B. Okay, so first off, we know for this example, we know that the FC prime, this one's different. This one's 3 KSI, and the FY is 60 KSI. And so remember, our goal is to try and design this beam, and by design we mean determine how much steel we need to put into the beam to adequately resist these loads. Okay? Now, typically for these problems, step one, well, it's not typically, it's always the case, is to compute MU. However, with this problem, I just gave it to you. So MU is 920 foot-kips. And if you refer back to example 10A, this took some work. Like, this took some time. We had to compute B and the self-weight, and then WL squared over 8, and 1.2 dead plus 1.6 live. But none of that would be different. So I don't really see any point in wasting our time. So I want to actually dig right into it. So step 2 is to compute MN required. And so that's MU over phi. And remember, in order to do this, we have to assume phi is 0.9. So that's 920 foot-kips over 0.9. And then let's go ahead and just do that now. By now, you should know that when we compute our MNs, that when we start plugging those MN values into design expressions, that they need to be in inch kips. Our beam dimensions are in inches. Our material stresses are in KSI, in inches. So let's just go ahead and do that now. So what does that come out to be? Like, it's snowing, it's Monday. Do we really have to break out our calculators? Yes, you have to break out your calculators. And that's inch kips. And you're good on that. Okay. Now, step 3. Now, I went ahead and told you that this was going to be a true T-beam. But if I didn't tell you, how would you know that this is going to be a true T-beam? Well, the answer is you don't. You got to figure it out. So the way that we figured that out, or the way that we do this, is we start off by computing a row required. And in order to do that, we assume it's rectangular. But then we take that row value and we plug it in to determine A to see whether or not that assumption is accurate. So we compute it, but then we immediately check it. And so I'm going to go through this a little fast because we've done this before. Okay, so that's 3 KSI. What was B? And what was D? Remember, that's squared. Got to bring your Casio FX115 ES pluses. Casio FX115 ES plus. Like, oh, it's Monday. I don't want to do this. Do we really have to? So what are we getting here? Like something like that? Do I have seconds on that? Remember, this is a complicated one, so this is one you're going to want to make sure that you get right. Okay? Now, remember, that is an assumption. Sorry. To compute that row value, we had to make an assumption. Okay? So we then need to verify that assumption right now. Now, in order to verify this, I have to compute A. I'm running out of room on this. Does everybody have this? Okay. Actually, no. I've got this extend page thing. Let's just do that. So let's compute resulting A. So the idea is we're going to back calculate what A would be if we use that row value. And so that's row FYD 0.85 FC prime 60 KSI, and that's 24 inches over 0.85 3 KSI. So somebody give me an answer. 4.05 inches. Do I have a second on that? Now, as a comparison, what is that value? 3. And so what does that mean? I was trying to get the answer. You're right. You're right. So we assumed that this is, you're not getting out of it. We'll find something else to ask. It's a simple formula, but it always works. So remember, we assumed that it was a rectangular T-beam, and we computed this row value. That we said, well, if we use that much reinforcement, what would our resulting stress block depth be? And that was this. Okay. Well, this doesn't work because for it to be a rectangular T-beam, this would have to be less than 3 inches because our stress block would have to go inside that flange. So we assumed it was a rectangular T-beam. That assumption is invalid. Okay. So therefore, assumption invalid. This is a true T-beam. Sorry. And so if we're dealing with a true T-beam, what we do is we skip 5, skip 6, skip 7, and move on to step 8. I'm going to extend this page a bit. So we go to step 8, and so what we do with step 8 is this. We start off with the flange couple, or the flange steel couple. All right? And so what we do with the flange steel couple is we compute two quantities. Okay? We compute ASF and we compute MNF. Okay, so let's take ASF first. So that's 0.85 FC prime B minus BW times HF over FY. Okay, and so that's 0.85, 3 KSI, 54 inches minus what was BW again? Somebody tell me. 15 times 3 inches over 60 KSI. And so what is that? Say it again. 4.9725. Do I have a second on that? That still isn't it, though. Hold on. All right, one more. We need to compute the MN, ASF, FY, D minus HF over 2. Okay? And so this is 4.9725, 60 KSI, and that's, what was D? 24 inches minus 3 inches over 2. And so what does this come out to be? And we'll leave it in inch kips for this point. Let's just leave it in inch kips. 6712.9. Do I have a second on that? Okay. Here's why we did what we did. So we know we're dealing with a true T-beam. Okay? So what we do is we say, all right, I'm going to compute these values first. Because look at ASF. Look at the computation. What do you have? You have FC prime, you have B, you have BW, you have HF, you have FY, right? None of those are a function of how much steel we have in the beam. Like if I give you this problem and I just say compute ASF and I don't ask you for anything else, you can do that, right? You just have to look at the beam and plug and chug, right? The same thing with MNF. Like once you have this value, you can do the same thing here. So MNF is completely independent of whatever steel pattern we choose to put in the beam. So what we're doing is this. We compute MNF first. And then what we do is we say, well, let's look at step 9. So step 9 is the web couple. And we say, well, we know how much we need for the whole thing. How much do we need for the whole thing? What was MN required? Does anybody remember that? Well, actually, we don't know. Actually, hold on. I'm sorry. I'm skipping ahead. I'm skipping ahead of myself. I'm sorry. I'm confusing you. Sorry. What's MU? What was MU? 920 foot kips. Now, how much is that in inch kips? Okay, so that's how much we need for the whole beam. All right, well, we know what we can get out of the flange couple. We can only get 6712.9 inch kips. And so we can look at this relationship and we can say, well, here's how much I need overall. Here's how much the flange couple can provide. What about the web couple? Well, I can solve for that pretty easily. How do I do that? Well, phi MN has to be greater than or equal to MU, right? Well, what's phi MN? Phi MN is phi MNF plus phi MNW. That's got to be greater than or equal to MU, right? Because I'm going to separate those into the capacity from the flange couple and the capacity from the web couple. So what don't I know? Well, I know I'm assuming phi is 0.9. I know this, and I know this, so I need to solve for that. So what do? Subtract, divide by phi, right? And that's what I'm doing. So MNW is MU minus phi MNF over phi. Yes? Yep, you're exactly right. But we're still in design mode. We haven't designed anything, so minus 0.9 times 12.9 inch kips over 0.9. And so this equals what? Inch kips. Now, add this number up and add this number up. No. Add this number and this number. It's not going to be 11,040. 12,266.7. Have we seen that somewhere before? MN required. So we could have done that too. I just kind of wanted you to see the whole kit and caboodle. Okay. Everybody with me so far? So now we can compute the amount of steel required for that couple. And now, how do we do that? Well, we end up using rho BD. We have to compute another rho value. Now, I want to show you what I'm doing here with this rho value because it's pretty straightforward. Rho required. And I'm computing a rho for the web couple. All right? 0.85 over Fy. 1 minus. And then on the bottom, I'm doing 0.85 FC prime, and instead of B, BW. And then instead of MN, MNW. Okay, and so this is 3 KSI. Now, for BW, instead of BW being the, what was it, 54? For the whole top flange, we're only looking at the web. So this is going to be 15. Don't forget to square that D. And then 2 times, what was this, 55, 53.7. And so, what does that come out to be? 0.0126. Do I have a second on that? Okay. Now what we can do is we can say, all right, ASW is rho BD. But remember, we use the rho BD and everything associated with the web. So and so that ends up being what? Say it again. 4.526. So we'll say 4.53 inches squared. Do I have a second on that? You're good. Okay. So, step 11. So now we can go into trial design. Now, refresh my memory. What was ASF? 4.97 inches squared. what was ASW? 4.53. So what that means is we have to choose a steel pattern that meets both those requirements. So add those up and what do you get? So we'll call that AS required. All right. 9 point, what? Yeah. ASF. You got 454? I got 9.5. Everybody okay with that? So here's the thing. That's a lot of steel, okay? That's a lot of steel to fit in a beam width that's only what? 15 inches? That's a lot. So here's what I propose is a feasible answer, okay? So here's the beam, right? And so this is B is 54 inches, right? And this is BW is 15. This is HF is 3 inches. Here is what I propose is a feasible answer. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I propose that a feasible answer is to use 10 number, getting ahead of myself, number 9s. So much so that AS is 10 square inches. Okay? Now, that measurement is going to be to the center of that steel pattern, and that is going to be my D is 24 inches. Okay? Now, remember that table where you look up minimum beam widths? Let me pull that up. Well, actually, do you want me to give you all a second? Do y'all need a second to draw this out? Okay, all right. Give me a sec. Let me skip on this. Here's our beam design aid right here. And so I propose that 10 number 9s work. However, when I go down here to look at the minimum web width, if I'm looking at number 9s, do I try and find for 10? No. What am I going to look up? 5. And so for 5 number 9s, the minimum beam width is 14.28 inches. Does that work for our beam? Yeah, that works. That works because we only have to consider 5 and the web width is 15 inches. So I'll put right here note for 5 number 9s, BW min is 14.28 inches. What do you think? Yes?
So if you found a pattern that's like more economical so the AS is lower, but say there was like 9 bars, would it still be better to go a little bit more if you found a symmetrical pattern?
Not necessarily. I mean, that's a possibility. You just, let me say this. I think there's something to be said about simplicity and repeatability. So let me give you an example, okay? And I'm trying to give you a little bit of a real world connotation to this. So how many of you have ever been in, let's say, a hotel where the lobby is really, really big and has a really big ceiling that probably spans multiple floors? How many of y'all have ever been in a lobby like that? So what you might have is, okay, here's the building, right? You know, here's the building, right? And, you know, there's floors like this, right? But then the lobby, like, hold on, let me add a little bit of depth to this. Okay, so here's the ground, but the lobby might actually be something like this, right? So the lobby extends like multiple stories, right? Make sense? Okay, so let's say this building goes on for another, 5 or 10 stories up, okay? One element in this building that the structural engineer is going to have to pay real close attention to is this one right here, okay? Because think, if this building goes up, another few stories, that beam is going to have a boatload of load on it, right? Because it's got to hold up the rest of that building, okay? And so we call this, there's a name for this in structural engineering, we'd call that a transfer girder. Okay? And so that transfer girder is basically, it's seeing like a column load directly on it. So this girder sees a lot of shear and a lot of moment. It's going to be a very specially designed element in the system. Whereas the 800 beam elements in the building that are just, like floor elements like here, they're just going to be regular old everyday beams. So to sort of go back to what you were saying, there's something to be said about repeatability. If this beam is going to be used 800-900 times in a floor system, just keep it simple, But if it's its own unique snowflake, maybe something like this, maybe it does need a little bit of love and attention. Does that make sense? Like unique snowflake, you like that? You like that? Okay. All right. Sound good? All right. Now, we're not quite finished because we got a couple other things that we need to consider, but I'm just going to have us list it out. So first off, the last step is to analyze the trial section. Okay. So it's already been mentioned, there's one assumption that we need to verify for this beam that we haven't yet verified. What would that assumption be? Phi. We need to verify phi is 0.90, right? So by connected to that, we also need to verify phi mn greater than or equal to mu, right? But there's two other limits that we need to verify. Give me one of them. I told you. I got one more I'm going to ask you. There's two more that we got to verify. Tell you what, I'll give you one of them, you give me the other one. We have to verify that the strain is greater than or equal to 0.004. What's the other one? No. You got a deal worked out with these people, don't you? To be continued. To be continued. Verify that the area of steel is greater than or equal to AS man. I'm not going to walk you through that because you all should know how to do that. That's simple. It's plug and chug. Sound good? Yes. Mm-hmm. Yes. That's a great question. What I would probably do for a problem like this is to assume that H is maybe like 4 or 4.5. So that's what I would assume. Like if I needed to update my loads, I might go with something like 1.5 inches. It's probably going to be less than that, but 1.5 inches is probably fine. Let me say this. If your bar size was only something like number 4s, you could very easily say, well, I'm just going to assume 1 inch, But number 9s, they're bigger around than 1 inch. So 1.5 inches is probably pretty reasonable. So if you need to update your moments, that's a pretty reasonable assumption to go off of. So there's that, but I wouldn't go crazier than that. So, yeah, that's a good question. Anything else? All right, I got time to talk about doubly reinforced, so let's talk about doubly reinforced. Okay. Okay, so let's talk about doubly reinforced. And just so everybody's clear, there's no such thing as triply reinforced or quadruply reinforced or anything like that. It's either singly or doubly, okay? And there's a reason why. It's because we're talking about the two fundamental types of forces that a beam sees internally. We're talking about compression and tension. And so a singly reinforced beam is what we've been talking about up until now. And so every single beam that we've been designing from day one up until now, we've only had reinforcement in areas of tension, okay? So now I want to consider a beam that has reinforcement not only in the lower part, but in the upper part. So we're talking about a beam that looks like this. So where we're considering not only the reinforcement in the tensile region, but the reinforcement in the compression region as well. So first off, like, I'll ask a simple question. Why haven't we been talking about that up until now? Well, it's not that it's like not something we need to consider.